Welcome to the video for Lecture 12, Section 2 for BBE 4023, Process Control and Instrumentation. This video continues with block diagram algebra begun last time. This time we will use block diagram algebra to reduce closed-loop block diagrams into a single overall transfer function. This slide shows a general closed-loop block diagram with four transfer functions, a comparator, a sensor, and a set point. The set point, in case you do not remember it from Section 4, is the desired process output value that the process user sets and inputs into the control system. This closed-loop system has a single loop. When we are done with this video, you will have seen the techniques to simplify or reduce that diagram into a single overall transfer function. We are going to present a couple of different ways to do this. I recommend that you practice the method using block diagram algebra. This is the first method. This method and the equation shown are used when there is a single loop and the loop has a comparator. When the loop uses a comparator, the loop is said to have negative feedback. The term negative feedback is used because the sensor and feedback element is subtracted from the set point input. The transfer function for this case, single loop with negative feedback, is lambda f over 1 plus lambda L. Lambda f is the product of the transfer functions in series between the input x and the output y. Lambda L, or lambda loop, is the product of all the transfer functions in the single loop. Let's look at an example. Here is a simple two-transfer function closed-loop negative feedback control system. It is a negative feedback loop because the small minus sign in the comparator where the B input is connected. Our task is to find the transfer function relating the output C to the input R. Using the single loop expression from the previous slide where C over R equals lambda f over 1 plus lambda L. Lambda f is the product of all the transfer functions in series between the input R and the output C. In this case, there is only one transfer function, function G. Lambda L is the product of all the transfer functions in the loop. In this case, there are two, G and H. So the result is G over 1 plus G times H. Let's solve the same problem using block diagram algebra. This is the technique I recommend using because it is a method that we will need to use when we develop overall transfer function for multi-loop systems. Our task is to find the overall transfer function C over R. Our block diagram is a simple two-transfer function closed-loop system with negative feedback. When we use block diagram algebra, it is recommended to start writing the equations at the output end. The first equation is C equals E times G. This means that the output C is the result of the input E going through the transfer function G. The next equation is E equals R minus B. This is the output of the comparator. The next equation is B equals C times H. This is the feedback element, and the input to the feedback element is the sensor reading C, and the output is B. Next we substitute the equation for B into the equation for E, then we substitute the equation for E into the equation for C. This produces the equation for C shown. After reorganizing, we get C over R equals G over 1 plus G times H. This is the same result we had on the previous slide. This slide highlights the fact that when we have a negative feedback system, that the denominator has a plus sign. This point is highlighted as a check on your answers. If the system has a negative feedback loop, there must be a positive term in the denominator. This slide shows a positive feedback loop. Both inputs in the summing point are positive. As with the negative feedback loop, the overall transfer function can be written in terms of lambda f and lambda L. The expression is G over 1 minus G times H. This slide highlights that with a positive feedback loop, the overall transfer function will have a negative term in the denominator. So when we have a positive feedback loop, the feedback input to the comparator B is added to the input R. There will be a negative term in the overall transfer function denominator. You might want to note that I am saying a negative term. My reason for saying it this way is because both of these examples were single loop systems. In the future, you will see multi-loop systems and there will be multiple terms in the denominator. And if one loop is a negative feedback loop, it will generate a positive term, and if one loop is a positive feedback loop, it will generate a negative term in the denominator. Now we have the tools to look at more complex closed loop systems. Here is a more general closed loop system. The output is C. There is a sensor in the output stream that is the input to the feedback element H. The comparator has a negative sign for the feedback B. The set point input is R. The difference between the measured feedback B and the set point R minus B, is the error E. This is the input for the first transfer function G1, and the output is the input for the transfer function G2. The output of G2 and a disturbance N are summed, and the sum is the input for the process transfer function G3. Sometimes, when working with a more complex block diagram, we will want to work with just a portion of the loop. One of the portions is called the open loop. We will assume that the disturbance input N is a 0. This is when you are interested in the output response of B to a change in the input E. We can write that as a transfer function B over E, which is just the product of the transfer functions in series from the input to the output, which in this case is G1 times G2 times G3 times H. Again, this is called the open loop transfer function. Here is another partial loop transfer function. It is called a feedforward transfer function. This is similar to the open loop transfer function in that the input function N is assumed 0 and the input function is the error function E. The difference is that the output is the process output C. Similar to the other one, the result of C over E is simply the product of the transfer functions between the input function E and the output function C, which in this case is G1 times G2 times G3. This brings me to the end of the Lecture 12 Section 2 video. Write down any questions you have and bring them up in class.